you'll typically see, you'll typically see user query, vector embedding, document retrieval, and LLM generation. So vector similarity search brings back the most semantically relevant text chunks. LLMs generate answers grounded in these chunks, reducing hallucinations. And it works well for many cases. Frequently asked questions, style questions, context-sensitive responses from domain-specific corpus. And RAG usually starts with a user asking a natural language question. And instead of relying only on the model's internal knowledge, we give it access to external information. So that's where this vector search comes in here. And both the user query and the documents in the knowledge base are converted into high-dimensional vectors, mathematical representations of meaning. So using similarity search, we retrieve chunks of text that are most relevant to the question. Then we have LLM generation. The large language model then takes those retrieved chunks as context. It uses them to generate a grounded answer rather than inventing one from scratch. We want to mitigate hallucinations. So the model is anchored in actual retrieved information rather than free associating. So some strengths and limitations. RAG is excellent for providing relevant context for a wide range of queries. However, it struggles with questions that require structured reasoning, like joining facts across multiple documents, or when the answer isn't explicitly stated in any retrieved chunk. So while RAG is powerful for retrieving relevant context documents, it can fall short when structured reasoning is required. And that's where knowledge graphs comes in, and they provide those explicit connections between the facts, enabling reason across entities and relationships that aren't contained in a single text chunk. GraphRAG builds on the RAG framework by adding a knowledge graph into the retrieval process. So why does this matter? Instead of relying on vector similarity to retrieve chunks of text, GraphRAG can also query the structured links in the graph. So this allows the system to pull in connected entities and relationships and not just isolated passages. How does this work? The graph serves as an additional retrieval layer. So when the user asks a question, the system doesn't just look for semantically similar text. It can also traverse the knowledge graph to bring back structured facts that are relevant. So some benefits to this is that you can fetch explicitly linked entities and relationships, and it adds that structured context alongside unstructured passages. This has a huge impact. The dual retrieval approach strengthens the LLM. It can reason both symbolically through the knowledge graph and semantically through the vector. Really, it's the best of both worlds, flexible language understanding from the LLM and precise structured reasoning from the graph side. This integration really opens the door for richer question answering and reasoning. And next, we're going to look at how GraphRAG actually works in practice and what kind of queries it's especially strong at handling. So for the GraphRAG pipeline, let's start with user query. GraphRAG really shines when a user asks a complex question, especially those requiring multi-hop reasoning, where the answer comes from connecting multiple facts. Context augmentation, instead of just feeding the LLM a chunk of retrieved text, we augment the prompt with both unstructured passages and structured knowledge graph facts. And this ensures that the model has the raw language context as well as explicit symbolic reasoning to work with. Dual retrieval, the system performs two retrieval steps in parallel. So one from a vector database to capture semantic similarity in documents, and another from the knowledge graph to fetch structured facts and relationships. And then we have enhanced response. So with the dual input, the LLM is better equipped to produce answers that are both fluent and factually grounded. So it's not just generating from memory, it's integrating symbolic reasoning with semantic understanding. So now that we've seen how the pipeline works, the natural question is, where does this approach really shine? So let's look at some more example scenarios where GraphRAG provides clear advantages over standard RAG. One benefit is structured reasoning. It's probably one of the biggest strengths of GraphRAG. And the knowledge graph can directly answer precise subqueries by following relationships. So something that's very difficult for an LLM alone, since it doesn't inherently understand that graph structure. Sorry, I didn't see the slide. Multi-hop questions. GraphRAG is also much more robust for multi-hop or complex queries. So an example, if you need to find authors who studied under a certain professor who later won a Nobel Prize, the graph can traverse those links directly, while vector search alone would likely miss that connection. Then we have exact matches, which is another advantage. Graph queries allow us to retrieve facts through exact matches, like a question, what is the population of France, while also navigating through relationships for context. Then we have combined capabilities. So the real power comes from combining semantic and symbolic retrieval by pulling both from a vector database and a knowledge graph. GraphRAG enables building systems that are fluent, context-aware, and logically precise. Okay, so we've seen how GraphRAG brings together the strengths of both vectors and graphs to handle complex queries. But to really unlock its potential in practice, we need to think carefully about how it's implemented. So things like hybrid retrieval strategies, graph depth, performance tuning. Let's dive into some more best practices for optimizing GraphRAG. Okay, so hybrid retrieval, vector, and graph. Why hybrid retrieval matters. It's one of the most effective best practices in GraphRAG is using both vector search and graph search together, and each method retrieves different types of information, and neither on its own is sufficient for all queries. Vector search excels at capturing semantic similarity. So it's great for pulling in unstructured text passages that are topically related to the query, and even if they don't match exact words. Graph search, on the other hand, leverages structure. So it can follow relationships and retrieve exact symbolic facts, like X is the parent company of Y. The key point is that graph retrieval should complement but not replace vector search. And by combining them, we can increase both recall and precision, pulling in a richer set of candidate facts while filtering for relevance. Of course, once we're combining vector and graph retrieval, another big consideration is how deep we go into the graph. So let's talk about graph depth and how to strike the right balance between completeness and efficiency. So when using a knowledge graph, it's important to limit how far we traverse from the initial entity. Unrestricted traversal can quickly become inefficient and often noisy. So in practice, most of the useful information is found within 1 or 2 hops from the entities mentioned in the query. This is usually enough to capture relevant connections without overloading the system. Going too deep in the graph can also introduce loosely related facts that confuse the model and slow down retrieval. So limiting depths keeps the results focused and ensures the LLM receives high-quality context. Once we've set the right traversal depth, the next consideration is how we store and index both our graph and our vector data. Proper indexing is critical for fast, scalable retrieval. So let's look at some best practices for indexing and performance. Okay, so for graph search optimization, efficient graph queries rely on proper indexing and constraints. So without them, traversals can become slow as the graph grows larger. Creating a full text index on entity names allows for fast lookups when matching a query terms to nodes in the graph. For vector retrieval, indexing the node embeddings enables rapid similarity searches, which is crucial for semantic retrieval at scale. Applying constraints on unique properties like IDs ensures data integrity and speeds up certain graph operations. So the takeaway here is that careful indexing across both structured graph data and vector embeddings prevents performance bottlenecks and keeps hybrid retrieval responses even as the data set continues to grow. So with hybrid retrieval, controlled graph depth, and optimized indexing in place, we're ready to see how these practices come together in a complete GraphRAG system and the kinds of results it can deliver in real-world applications. So let's dive into the scalability and cost considerations. Okay, so thoughtful schema design is key for scaling knowledge graphs. We want to avoid overly dense nodes or supernodes that connect too many entities because it will slow down queries significantly. We want to keep the graph focused on facts that actually add value to the retrieval. Don't try to include every trivial detail. Irrelevant data will increase noise and add to the computational cost. Constructing the knowledge graph, especially when using LLMs to extract facts, can be expensive. So it's really best to build or update the knowledge graph offline or asynchronously rather than doing it during every user query. And then caching strategy for frequently queried subgraphs or commonly accessed paths. Caching can dramatically increase performance and reduce computational costs. So with careful schema design, focused content, and smart offline processing and caching, GraphRAG can scale very efficiently. So let's dive a little deeper into nodes, entities, edges, relationships, and structured navigation. We've talked about these things a little bit. So in a knowledge graph, nodes represent the things we care about: people, places, concepts, products, or really any real-world entity. Each node is a distinct object within the graph. The edges represent the relationships or connected nodes and describe how two entities are related to each other. So we have an example of Alice acted in a movie. So these connections can be directed and often have inverses. So like movie has actor Alice. Structured navigation shows how these interconnected entities mirror real-world knowledge, allowing us to traverse facts systematically. And by following those edges, we can reason across multiple nodes and uncover relationships that aren't maybe immediately obvious to someone looking at the data as a first glance. So the takeaway here is that understanding the structure of nodes and edges is fundamental to leveraging knowledge graphs for retrieval, reasoning, and building more intelligent systems. Okay, so attributes, nodes, and edges can have attributes or properties. For example, a person node might have a birth date or nationality as attributes, and these provide additional details about each entity. And then triples for every fact in a knowledge graph, it's represented by a triple usually. So subject, predicate, object. So we talked about some of these examples. Paris is capital France, or Paris population 2.1 million. So many knowledge graphs follow standard resource description framework, so RDF, to formalize triples. And this defines the predicates and relationships which ensures consistency across the graph. So triples and attributes give knowledge graphs their structure and richness, making them both human readable and machine actionable. So now we really have the building blocks for how these graphs feed into retrieval systems, and this sets the stage for combining knowledge graphs with LLMs in GraphRAG for structured multi-hop reasoning. So, excuse me, an ontology is a formal schema that defines the types of entities relationships, and rules for how they can connect. And this is essentially the blueprint of your knowledge graph. Taxonomy is a hierarchical categorization, often expressed as is a relationship. For example, cardiologist is a subtype of doctor. And then with a well-defined ontology, we can perform inference. So a reasoner can deduce new facts based on the rules defined in ontology. So for example, if X treats Y and X is a cardiologist, then X is a doctor. And we can infer that based on knowing that X is a cardiologist. Ontologies can also define which relations are valid between entity classes, like treats being allowed from a doctor to a patient. So this provides the structure and rules that make knowledge graphs powerful for reasoning beyond just storing raw facts. Okay, so there's several approaches to constructing a knowledge graph, depending on the domain, the data available, and the resources at hand. So first one is manual curation. In this approach, domain experts define the schema and carefully input data. So for example, a company might integrate its product catalog, customer data, and support records into a product knowledge graph. And the advantage here is high accuracy, trustworthiness, since experts control the process. The next one is automated extraction. So this is another path using NLP or LLMs to automatically extract entities and relationships from text. So tools like LangChain's LLM Graph Transformer can read unstructured text and output structured entities and edges. So this is much faster and scales well, though the trade-off is that the results need validation to catch any errors. And then the last one is crowdsourcing. So this is a third option that is collaborative, community-driven construction. Products like Wikidata rely on contributors worldwide to add, edit, and curate facts, and this approach enables coverage at a scale that individual organizations could never achieve on their own. So in practice, many organizations use a hybrid approach, combining expert curation, automatic extraction, and community input to balance quality, scale, and coverage. So knowledge graphs are powerful, but like any technology, they come with both advantages and challenges. So first, with some advantages, they provide an explicit structure and semantic context. So relationships are clear, making data easier to reason over. They improve explainability. So if an answer comes from the graph, you can trace exactly which nodes and edges were used. They allow exact matching and logical constraints, something vector search alone can't guarantee. And they're very strong for structured reasoning, like tracing causal links and enforcing time-based constraints. So some challenges, constructing them requires significant effort, both to create the graph initially and to keep it updated. And when using LLMs for automated extraction, there's always a quality control challenge, so ensuring extracted entities and relationships are correct. With very large graphs, performance can become an issue. Querying billions of nodes and edges efficiently is definitely not trivial. Schema design can also be complex, so defining the right entities, relationships, and constraints require careful planning. And finally, privacy concerns arise if sensitive, personal, or organizational data is connected in a way that could expose unintended insights. So the real art is balancing the benefits of structured reasoning with the cost and complexity of building and maintaining the graph. So knowledge graphs are widely used across industries and everyday tools that we interact with. In search engines, they power direct answers in knowledge panels. For example, Google's knowledge graph contains over 500 million entities. For recommendation systems, graphs of users, items, interactions, help platforms suggest relevant content. So whether it's movies on Netflix or products on Amazon. In personal assistants like Siri and Alexa, knowledge graphs are key for answering factual queries in a conversational way. In healthcare, they integrate medical research, patient records, and clinical knowledge to help support decision making. Finance, knowledge graphs are used for anti-money laundering, risk analysis, and fraud detection. For example, mapping suspicious financial transactions into fraud rings. And within enterprise data, also, they connect siloed sources like customers, product, sales, and support tickets, making it easier for companies to understand their business holistically. Okay, so now that we've seen where knowledge graphs are applied, let's take a closer look at one of the most popular technologies for building them, Neo4j and its property graph model. So Neo4j is the leading graph databases. It uses property graph model. And in this model, we have three components. We have nodes, which represent entities and have one or more labels to define their role or type. Relationships, which connect nodes with specific types. And then properties, which are key value pairs that can be attached to both nodes and relationships, giving them context and detail. So a big advantage over RDF triple stores is flexibility. Neo4j's doesn't require a global ontology upfront. Instead, you can start loading data immediately and then only later enforce those constraints or introduce a schema if needed. And when we dive into the demo, you'll be able to see this actually in practice and how the schema is working. So Neo4j is queried with Cypher, which is designed specifically for working graphs. And it looks a little bit like SQL if you're familiar, but it uses ASCII art syntax to make patterns visually intuitive. So we have some examples here. We can look at a person, name Albert Einstein, subject physics. You can see just similar to SQL, you can kind of read it like an English sentence. But here we have a person, friend of person B, and that represents two person nodes with the friend of being the relationship between A and B nodes. Okay, and then also this merge keyword right here is creating data. So in this first one here, we're adding Albert Einstein, the subject of physics, and connecting him both to physics studied and to the Nobel Peace Prize in Physics won here. And then second, the match is also using, also querying the graph. And in this case, we look up Einstein and return the prize that he won. So now that we've seen how Neo4j's property graph and Cypher work, let's contrast that with another major approach to knowledge representation, the RDF and semantic web stack. So the RDF model represents data as triples. So we've talked about this subject, predicate, object. We have an example of city is capital of France. To query that RDF data, we use SparkQL, which is somewhat similar to SQL, but designed for matching triple patterns. RDF graphs can also have formal ontologies defined with the web ontology language here, OWL, and its interoperability. They're great for integrating data across organizations where shared vocabulary and ontologies are needed. By contrast, property graphs like Neo4j are often more pragmatic and developer-friendly for rapid applications. So the choice between RDF and property graphs often comes down to the project needs, integration heavy versus application focus. So knowledge graphs and RAG integration. When a user question comes in, the system first pre-processes it to identify entities mentioned. Then it uses a knowledge graph query, retrieving the subgraph neighborhood around those entities to gather the structured facts. And then in parallel, the system performs a vector search across embeddings of unstructured text, pulling in relevant passages. Next, GraphRAG Retriever combines both that structured graph data and the unstructured text into a unified context. Finally, the LLM generates a response constrained to that curated context and ensures higher factual accuracy and avoids hallucinations. This approach leverages the strengths of both worlds, structured precision from the graph and rich coverage from unstructured text. So to connect the user questions to a knowledge graph, we need to extract the entities being mentioned. So the process typically works like this. First, we maintain the conversational history and use an LLM to rephrase follow-up questions into standalone questions. Next, we use a prompt with the LLM to extract entities. So, for example, recognizing Einstein as a person or a Nobel Prize in physics as an award. Then we search the knowledge graph for the nodes that match those extracted entities. And then finally, we traverse the graph to gather relationships and neighbors, building a small subgraph around the entities. And this result is a contextual subgraph, which serves as the structured foundation for answering the user's original question. Once we've extracted the entities and receive a subgraph, the next step is to combine that structured knowledge with unstructured text, and that's where hybrid retrieval comes in. So hybrid retrieval means combining structured graph data with unstructured text data. So the pseudocode here shows the flow. First, we called a structured retriever to pull up relevant facts from the knowledge graph. Then we use a vector search to retrieve similar unstructured passages. And then finally, we concatenate the two into a single context. The compiled context might include structured knowledge and then the unstructured passages shown here. So together, these create a richer, more reliable context than either source alone. So why does this hybrid approach actually make a difference? Let's look at what structured knowledge brings to the table. So there's a few key advantages of injecting structured knowledge into the retrieval. One is explicit relationships. So graphs capture links like Augustus became emperor 27 BC, which aren't always clear in text. There's also no missing facts. So graph traversal ensures that we don't miss that key information, unlike embeddings, which may skip over relevant text. Reasoning power. So with structured knowledge, the LLM can chain relationships to answer complex queries it couldn't solve from the text alone. And then enforced constraints. Graphs can apply rules, so such as time ranges or valid relationships, which vector search cannot guarantee. So in short, hybrid retrieval allows us to combine the precision of structured data with the richness of unstructured text, making the final LLM response more accurate and trustworthy. Yes. Okay, great. Okay. So before we dive into the demo, here are the skills, tools, and setups you'll need if you want to follow along, or you can also try this yourself or play around with it afterwards. And once the slides are shared out, you can head over to this GitHub page right here, and that's the demo we'll be walking through. All right, so skills and knowledge. Python programming language, if you're comfortable with it, or at least you can read it, you don't need to be an expert, but you should have version 3.8 or higher installed on your computer. Basic understanding of LLM APIs and how to call them. Familiarity with LangChain, we'll be using it to orchestrate the workflow. Having some background in embeddings and vector search is helpful, but if not, you'll learn as you go. And at least a basic grasp on databases and graph concepts, and we'll be using Neo4j. You can have local or a DB set up. You can set up the free version of AuraDB, which I did. I think there's like a 14-day trial you can do as well for the higher version, and it gives you those connection credentials you'll need for Neo4j, and then you'll also need the OpenAPI key access, which you can also get for free by creating an OpenAI account and generating that secret key that you will use in your environment file. So this is what you need. Once you have the prerequisites ready, the next step is setting up the project environment. So first, you're going to install the dependencies listed in this requirements.txt. If you're not following along exactly right now, don't worry. This can be done later on, and I'll kind of show you too what I did locally. But it's okay if you're not keeping up to this point locally right now. In this environment file, it basically just has the URI for Neo4j for your database, the username and password for your database credentials, and your OpenAI key that you can generate from your account. So for the demo, we'll work with a knowledge source. There's a few different examples in the demo. So the first one we'll talk about is the Wikipedia article on the Roman Empire and related pages. So the goal is to let an LLM answer historical questions, but with an important twist. Instead of relying on only the text, we'll combine graph retrieval with unstructured passages. And I know there was a question actually about combining structured and unstructured. This will show you exactly how to do that. So this setup mimics a real-world scenario. So imagine you already have a large text knowledge base, but you want to make your system more reliable by enriching it with a knowledge graph. So by integrating the Roman Empire knowledge into both a vector store and a Neo4j graph, we'll be able to show you that hybrid retrieval GraphRAG to improve factual accuracy and reasoning. This is really a perfect use case too, because the Roman history is full of explicit relationships. So emperors, battles, successions that a graph can capture very clearly. So let's jump into it. First step of the pipeline is pulling in source content. So here we're using LangChain's Wikipedia loader to grab the article on the Roman Empire and some related pages. Once the raw text is loaded, we split it into chunks, so 500 tokens each with some overlap. And we're chunking because LLMs work best with smaller focused inputs, and overlapping helps preserve continuity between chunks. And each chunk is then stored as a document object, which makes it easy to pass into downstream processes like embedding, vector search, or graph extraction. And this ensures that each piece of text stays topically focused. So, for example, one chunk may deal with the founding of the empire, and another with Augustus, and another with the fall of Rome. And we're talking about this in the slides, and then we're gonna jump into the code and actually run it with a different example. Okay, so now that we have clean text chunks, the next step is to generate a knowledge graph from them. Once extracted, these nodes and edges are pushed into Neo4j, giving us structured representation of the Roman Empire domain. And over multiple chunks, the graph grows, linking people, events, and places into an interconnected knowledge base. So generate knowledge graph from text. So we'll use LangChain's LLM graph transformer, taking the unstructured text chunks and automatically extracting the entities and relationship. For each chunk of text, we will output a structured representation, essentially a set of nodes and edges that capture the meaning in the graph. We have an example here. So if the text says Augustus defeated Mark Antony, then the transformer recognizes the key entities and their relationship, and it generates nodes for Augustus and Mark Antony, both tagged as person here, and a relationship is defeated from going from Augustus to Mark Antony. Then we populate Neo4j with these nodes and relationships, gradually building a rich graph representation of the knowledge contained in our source documents. Okay. I'll share the GitHub link when I jump over to the code as well. Let's see. Okay. So let's walk through a simple example query. So who was the first Roman emperor? The system works in several steps. So first, it identifies the key entity. So in this case, first Roman emperor, which maps to Augustus. A graph query against Neo4j retrieves structured facts about Augustus, such as Augustus' full name, Augustus' successor. At the same time, a vector search retrieves unstructured passages describing Augustus as the founder and first emperor of Rome. And then the LLM then combines the structured and unstructured context to generate the answer. So the final answer is simple and accurate. Augustus was the first Roman emperor. Okay, so now let's see a multi-hop query. So a follow-up question, when did he become the first emperor? Here, the system needs context from the previous question. So he then refers to Augustus. So the LLM first reformulates the question into a standalone version. So when did, instead of he, it will be Augustus become the first emperor. Next, the system extracts Augustus as the entity and queries the knowledge graph. So the graph might return Augustus, start of reign 27 BC. Simultaneously, vector search retrieves text chunks confirming this date. So the example passage here might contain in 27 BC, the Senate granted Octavian the title Augustus. So combining both the structured and unstructured evidence, the LLM produces the precise answer of 27 BC. So in addition to historical data, knowledge graphs are extremely valuable in domain-specific settings like healthcare. So the goal of this demo is to show you how a healthcare knowledge graph can enable structured querying of medical facts, patient data, or research findings, and support reasoning by connecting entities such as drugs, diseases, symptoms, and clinical guidelines. So we'll jump into the code here. Here's the link again if you didn't see. Let me see if I just make this. I might have to reshare the correct page. 1 second. Okay. All right. Okay, let me send. Oh, thank you for whoever sent that in the chat. Can everyone see my screen here? I have my VS Code open and the GitHub page open. Yes, okay, great. Okay. So let's start with the configuration step. So here is the GitHub page that we're talking about. There's a few different packages here, one for healthcare, one for prepping the text for RAG, one GraphRAG, and one simple knowledge graph. All good things to explore. You'll also want to create your .m file here where it tells you exactly what you need to configure your instance here. So what I did was created on Neo4j, I did, instead of local, I created this Aura DB, which you could also create like a local DB version. I think it's kind of cool to explore this UI. There's lots of capabilities here. But if you just create a free account, you can create your instance, which if I go to my instances here, you'll see I have this instance one running. It has the ID here, and you'll also be able to when you create it, it gives you all of the configuration things you need, like username and password, or you can leave it as the default. And then you could go to query here, and this is where this cipher querying is going to happen, which I'll show in the code. But if you're trying to kind of play around with it locally and look at all the scripts that this project here provides, you can actually go into your instance here and actually connect to whatever you created and then run any queries you want. And there's some really cool options here. You can actually click this generate query button and you can describe the query you want to generate and play around with it there. It's good to get exposure if you haven't used it before. And also when you're trying to debug locally or try something out, you can first try your query on your instance here. The other thing you can do is import your data. So this GitHub project provides you a CSV file for the healthcare part of it. And you could take this CSV and actually import it to your database and automatically create a schema from it. Then you can also update it and change it in any way you want. I've edited it a little locally just to play around with different results. And I'll show you kind of what that looks like. Okay. So that's in general my setup. Let's start with this prepping text one. Or no, actually, let's start with healthcare. Okay, so let's look at the code first. Okay, so here we have loading our environment. Here's my .mv file right here. We have this Neo4j graph, and then you'll see all these cipher queries defined. There are comments here of what this is trying to do, but they read similar to SQL, and you can note it. You can probably understand what the query is doing just by reading it. And then there's also some comments there. So here's some of the cipher queries for the healthcare Python file. So the first one, match only the provider nodes by specifying the node label. And then we have return the names of healthcare providers. You can see they're pretty straightforward. Limit 10, very similar to SQL. So basically, the graph here is storing a mini healthcare network where providers, patients, specializations, and locations are all connected. And so the output is simply answering all these cipher queries that are written in this file, showing who treats who, what they specialize in, where they're located, and patient conditions. So we can see here, actually just ran it, but I'll show you how to run it. So just running Python healthcare, and then this specific healthcare lang chain file here will query my Neo4j database, and it will turn here 27 nodes in this graph, 5 healthcare providers. You can see it lists the providers, it lists all the patients, specializations, locations, and then it starts to combine, like if we look at this patients treated by Dr. John Smith, we can take a look at what this query is. Let's see. Here we go. So we have matching the healthcare provider, Dr. John Smith, treats, patient, and then we want to return all the distinct patients. So we'll see here we have 2 patients listed treated by John Smith. Similarly, we'll do same thing for specializations and locations. So you can kind of get a sense of the different relationships between these entities and then how these cipher queries work to return our results here. Okay, so that's kind of step 1. Digging a little deeper, we can go into this prep text for RAG script here. And I think when you clone down this repo, some of this stuff will be commented out. So just uncomment it because you want to create this vector index. I'm not sure why it's commented out, but just uncomment it, and then you can see that your index was created. You want to create this vector index health providers embeddings in Neo4j to store the embeddings of provider bios. So you then encode each healthcare provider bio into a vector using GenAI vector encode. So right here. And then the vectors are saved into a property. And then that's on each healthcare provider node. And then when we're actually going to run our script, our question here, give me a list of healthcare providers in the area of dermatology. The script encodes that question into a vector, which is here. This GenAI vector encode with the question. It queries the health provider's embeddings index using cosine similarity. And then it returns the top 3 most similar provided bios to the question vector. So with this specific question, give me a list of healthcare providers in the area of dermatology. Let's run it. So move Zoom out of the way. So we're going to run this app.py file. This warning is just because of my versioning of this URL lib3, but it shouldn't actually impact anything. And this is actually going to be using your OpenAI key that you defined earlier on. So that's, if you create the free account, you can go to your settings, and then I think there's a section for developer, and you can generate a new API key. I think right here, yeah. API key, you need that there for this to work. So we see this output. Let me zoom in a little bit to see. So we have a score here with a name and then the bio. So what does this output mean? So Dr. Jessica Lee shows up first. Her score is here, 0.897. And that's because her bio contains dermatologists. And that's exactly, it's semantically closest to the query about dermatology. Then we have Dr. Sarah Johnson coming up next, I believe. Yeah, next. And then Dr. Emily Davis in third. So we have a pediatrician here and a neurologist next. Slightly lower scores, but their bios contain concepts that embeddings think are somewhat related to the query, but are not as strong of a match as Dr. Jessica Lee. So the score is the similarity value from vector search. So cosine similarity in this case, and it ranges from 0 to 1. So closer to 1 means that it's more similar. So this 0.897 is a very close match. And then that means that the query engine thinks Dr. Jessica Lee is the best dermatologist match, but also the other two are related. So one thing here to note is that we have a really small data set. If we look at this CSV, 101 lines, there's not a lot here. We could actually have more added here, and there'll probably be some different results. You can kind of play around with that and use different data sets. And then, you know, we also can play around with different questions that we ask. So in this app file here, you can play around with this, query for different things, try it out, and see what comes up. You'll get to kind of analyze your results there. But in this case, the query worked correctly, and it pulled the most semantically similar bios to dermatology, and the scores show relative closeness, but good that dermatology was ranked number 1. And so this is kind of how to interact with this project. There's lots more you can do here, and there's lots more you can do with Neo4j. Just showed some of it, but there's also visualizations here you can do, or go to this Explore tab, and there's a lot more you can take a look at. But you can play around here with editing your schema, importing different data, rerunning your scripts, seeing how that changes things. And this is kind of a good way to learn and practice.